Welcome to another short video in which we're going to this time discuss Coulombs Law. This is something that I'm sure a few of you are familiar with from high school physics, but we're going to go into a little bit more detail and try and work out in this video how do you do an application, how to actually do a calculation using Coulombs Law when things are not necessarily just in a single plane or a single direction. So this is just a little bit of a reminder. What is Coulombs Law? Coulombs Law tells us about the force between any two charges. So in this case, I have a charge A, which is some positive charge. It doesn't have to be, of course, and some charge B, which is a negative charge. As hopefully you know, these two charges being oppositely charged will actually try and attract one another, and they'll have a force that's attractive between them. And the magnitude of that force, of course, a force is a vector, the magnitude of that force is simply given by this equation up here. So K is a constant of proportionality, which we'll discuss in more detail as we go through the course, and if you want to know more about it, then I recommend reading it in the textbook. Q is the size of charge A, and QB is the size of charge B, and RAB is just the distance between the two charges. So this is, for example, the force that charge B feels from charge A, okay? And notice that it goes like 1 on R squared, or 1 on the distance squared. So this is Coulombs Law. Just a couple of things to note. This is actually clearly a vector. And one of the things that this means is that vector addition rules apply. So if I have multiple charges, as is the case here, so I've got multiple charges, I've got I different charges, then the net force given by, the net force on any given charge is just equal to the sum of the forces from the individual charges. So in that way, if I have a very complicated system, I can still work out the force on any given charge just by calculating the sum of all of the forces in the nearby. So we're going to do this little example here, and what we want to do is we want to calculate the force on this charge up here given all of these other charges. So we've got 3 different charges that are imposing a force onto this charge little q up here. So you can see that there's a single minus q value worth of charge minus capital Q charge over there, a single minus capital Q charge over here as well, and a whopping 4q of charge over on this side here. So we want to calculate the force on this q here from all of the other ones. So what we can start off doing is we want to calculate, because we can sum additionally from each of these other charges, is we can calculate from just a single one and then sum the forces from all of the other ones as we go. So just for a little bit of simplicity, what I want to do is I want to label these. I'm going to just, for the sake of argument, label this A, label this charge B, label this charge C, and label this charge D, okay? And the reason I want to do this is that now I can write, for example, the first thing that we're going to calculate is we're going to calculate the force on charge A given charge C, okay? So this is the force on charge A given this charge C. Now, we're just going to worry about the magnitudes of these forces. So if I want to calculate the magnitude of this force, then the force on A from C is just equal to K multiplied by the size of this charge, which is 4Q, multiplied by the size of this charge, which is little q, all divided by the distance between this charge and this charge squared. Okay, so the distance between this charge and this charge, well, the distance is the square root of L squared plus L squared, okay, and that's all squared. So in other words, this thing just becomes, I get L squared plus L squared is 2L squared. It's in a square root, but then I'm squaring, so all I end up with is a 2 on the top, cancels with that, Q, I've left off my K, so let's put it out of order, on L squared. Okay, so this is the force that A feels from C. And one thing that we want to do is we notice that this B only applies a force on A in this direction, okay? So let's label that direction the X direction. X, which means we're going to label this direction Y. We could choose to do this in any way, but this is just for convenience. And the reason that I want to do this is now I want to ask, what's the magnitude of the force of AC in just the x direction, because I'm going to then just calculate all of my forces in the x direction. You can see that this charge D doesn't contribute in this x direction, it only contributes in the y direction. Okay, so the charges in the x direction are going to be from B and C. So I can calculate the force of AC just in the x direction, and of course this is just the total force AC multiplied by cosine theta, where cosine theta is of course the angle that is made between that and that. So this cosine of theta is 45 degrees because we have a perfect square. Cosine of 45 degrees is root 2 on 2. So this introduces another factor of root 2 on 2. So I get root 2 divided by 2 multiplied by this 2kq. Am I going off the screen? Maybe. On L squared. My 2's cancel. Okay. And I end up with just square root square root of 2 k big Q little q on L squared. Great. So this is the force on A from C, just in that x direction. Likewise, we can calculate the force on A from B, which is all just in the x direction. So the force on A from B is just equal to, of course, K times the charge up here, which is minus Q, so we get a minus Q this time, times little q, divided by the distance squared, and of course the distance between these two charges is L squared. And the whole point of this is now I can say the total force, so remembering that this is just in the x direction, okay, because that's the only component there. Now I can say that the total force, F, let's call it F tot, in the x direction, okay, is simply given to the sum of these two. They're the only forces in that x direction, so I can simply add those two vectors. So it's A, B in the x direction plus F, A, C in the x direction. And I can add these two things up. I'm required to do a little bit of algebra, which I'm not going to bother doing for you because I figure you guys can do that. But you can see that there are common factors here. I'm going to end up with a K, Q, Q divided by L squared. And then I get, there's a square root of 2 minus 1. In fact, that is all of the algebra. Again, my minus 1 might have gone off the screen, and I apologize for that. So you should be able to look at this problem and simply write down for me what is the F tot in the y direction. Okay, F tot in the y direction is simply exactly the same because this problem is symmetric about that 45-degree axis. So I can simply write this down. F tot in the y direction is the same. Of course, this is going in y direction rather than the x direction of L squared, square root 2 minus 1. And of course, the final step is I want to calculate the magnitude of the total force on this object. The magnitude of the total force is just the sum of the squares of the of this thing. Okay, so I can finally write F tot, and remembering I've been very lazy and